Hey, kids. Well, today, or at least right now, I'm going to talk to you guys, to give you a general overview of simple harmonic motion. So there's going to be two basic types of simple harmonic motion that you're going to be expected to know about. One would be something like this, where you have a mass on a spring and it's moving back and forth, or you have a pendulum and it's swinging back and forth, back and forth. And yes, if you look on your formula sheet, there's a formula for the period, which is this 2 pi square root of m over k. And if you think about this equation, it should totally make sense to you guys, because look, if I make this mass bigger, more inertia, harder to accelerate, more time to go back and forth. Bigger number, more time to go back and forth. Yeah, that makes sense. Okay, if I make this number bigger, this is how stiff the spring is, you're going to get a bigger force. Well, if you get a bigger force, you're going to get more acceleration, therefore it's going to take less time to go back and forth. Bigger number here, and then you're going to get a smaller number there. Yay, makes sense. With a pendulum, and actually, if you look on the formula sheet, it says this to even remind you, hey, look, period of a spring. And then over here, they do period of a pendulum. And this is L over G. Okay, so that, and again, this should kind of make sense. We have already done rotational stuff. So if you think about rotational inertia, that if my length is bigger, okay, hey, I'm going to have a bigger rotational inertia. More rotational inertia, harder to change its state of rotation, meaning it's going to take more time to go back and forth. Bigger period, okay? This is related to the force of gravity, which is going to be like called your restoring force. Well, and here on Earth, G is always going to be the same, but if you were to go to some other planet, for example, where G was different, or you go to the moon where G is different, then you know what? The restoring force, the force that's causing it to, go back and forth, okay, is going to be bigger or smaller. Well, if G is bigger, that's going to be smaller. That should make sense because it's going to go back and forth, in less time. If G is smaller, then that will be bigger. So there you go. That's kind of some of the basics. But let's go back to this one, because most of your graphs and questions and stuff all relate to this one. So if you have, for example, okay, let's say, for example, you guys have a question that's like, hey, where are you going to experience the biggest acceleration? Well, if it's something like that, acceleration, draw your FBD. If you draw your FBD right here, this is when it's in equilibrium, okay? This is where the spring is not stretched or compressed. So I have the force of gravity, the normal force. There's no other force acting. If there's no other force acting, then there is no acceleration when it's equilibrium. But when you're all the way at here or here, okay, let's say, example, we're going to do right there. If I was to do at this point, I have the biggest force of the spring. Remember, force of the spring is equal to K times X. Okay, so then this would equal M times A, and I would have the biggest A. Hopefully you can see that. Hey, look, now you can see that. So there you go. Same thing over here, just the force is pointing in a different direction. That should make sense. You may have questions about, hey, find the speed. Okay, again, this is not anything new. This is just conservation of energy, okay? So if I label my points, remember doing conservation energy, draw your picture, label your points. If I say A, B, C, so let's say A is when it's most compressed, B is when it's in equilibrium, let's say C is some point, in between B and D. D is going to be where it's, the most stretched out, okay? And let's say there's an example where it's like, hey, find the maximum speed. Okay, well, maximum speed would be at B. Hopefully that makes sense, most kinetic energy. And then you'd want to set up your just conservation of energy. And you'd go, all right, well, what type of energy do I have at A? Well, yeah, I have potential energy of the spring. Well, actually, we should probably say what our system is, and it's going to make sense to make our system include the spring and the mass. I think that would make sense, right? But then it'd be you would just have kinetic energy if there's frictionless. If we say this has no friction, then we don't have to worry about any work. And so you have this. So then you would set it up. 1/2 kx squared equals 1/2 mv squared. Okay, and you could solve for stuff. Hopefully it makes a lot of sense. There might be a question where it's like, hey, if I compress it twice as much, what's going to happen to my speed? Or, something like that, And the answer to that question is, well, if I compress this twice as much, okay, if you look, this is proportional to this. So you would get x squared is proportional to v squared. Well, which means x is proportional to v, which means if you compress it twice as much, it's going to be 2 times the speed. But yeah, so, hopefully that should not be a problem. If you're doing a problem where it's like, hey, how fast is it going at point C, which is in between, then hopefully you would realize you're going to do this, where it's some new US plus K, and then again, it's just plug stuff in and solve. Maybe there's going to be a graph, okay, as far as the graphs you could see. You could see a displacement versus time graph, okay. Hopefully it makes sense, a displacement versus time graph. If I start here at time 0, that's a really not simple harmonic motion because there's not going back and forth. It's just going to sit right there. So like at time 0, I'm going to have to either smush this or stretch it. Well, let's say I smush it, and let's say I call this way positive. Well, if I smush it, then I'm starting in negative, and then just do your points. So like, well, at some point, it's going to have 0 displacement, right? At some point, it's going to have maximum of, at point D, it's going to be there. At some point, it's going to go back. At some point, it's going to go back. And then it's like, well, is this going to be a line? Well, is it constant motion? I think not. So then it's like, oh, well, that means going from here to here, it's speeding up going forward. B to D, it's slowing down. So this would be like A, B, D, C would be like something in there. Okay. And then I'm speeding up going backwards, slowing down forward. Okay. So again, just do your basic points and solve. That looks a little bit better. And then if I wanted to do a V versus T graph, okay, V. Again, start with the points you know. Okay, well, where is it not moving? Oh, at A, at D. So then at A, actually, I'm going to do it this way just so you can see it. I'll put it right on top. Okay, so at A, it's not moving. At D, it's not moving. At A, it's not moving. So start with those points. Those are the points you know. And then it's like, all right, so then if you take a look at the way this graph is set up, well, which way am I moving? Oh, I'm moving in the positive direction, positive slope. You can see that my slope is getting more steep. So then, oh, that means I'm going to reach a point where I'm going to be at my maximum. Okay? And then now with this graph, you might go, well, wait a second, is it linear? Well, and hopefully you didn't memorize this because, in our unit 1, we always did linear V versus T graphs. Well, guess what? The acceleration is not constant. Why? Because it's not a constant net force here. Okay? You exert more force, the spring exerts more force here than it does there. So draw out your graph. It would look something like this. Okay? And then your A versus T graph. Okay? Again, that should be same difference. So where is it 0 acceleration? Oh yeah, when it's in the middle. Where is that? That's at B. So label your points. Right here. Okay? And then draw it in. And then let me do this so you can actually see it. Sorry. And if you look, hey, I have a positive slope, so therefore I have a positive acceleration. Positive acceleration. And it's getting less steep, so that's why it's going towards here. And it is changing, so if I just draw it, it's going to look like that. Okay? But hopefully that, again, don't make it harder than it is. If we had a graph where it's like, hey, I want to graph the potential energy, because you might. Okay? If I want to graph potential energy, of my system here. Okay? Well, what type of potential energy do I have? All I have is the potential energy of my spring. Well, again, if you think about this, if I compress this Am I at 0? No, of course not. If I compress it, I am going to be at lots of potential energy. Okay? And then I'm going to go to a point where I'm at 0 potential energy. And then I go back to lots of potential energy. And then I go back to 0 potential energy. Okay? And then, because hopefully this should make sense to you, so that if I was to draw this out, la 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 la, okay, something like that. Okay? Versus if I was graphing kinetic versus time, well, I know kinetic plus potential has to be constant, because if I was going to make a graph of mechanical energy versus time, it would look like, yeah, okay, because it's constant the whole time. So it's like, hey, at A, I'm at 0, right? Okay. At B, I am at my maximum. And then it's like, well, geez, this plus this has to be a constant, so then I need to kind of make the inverse of that graph. You know, oh, it has to be back to 0, so go ahead and, hang on. And then I would go back like this. Okay. But hopefully, again, should make sense to you guys. You're never going to get negative y 1/2 kx squared. Never going to be negative. Kinetic energy, you can't have negative kinetic energy. So anyway, hopefully that makes sense. Bye, kids.